Most reptiles head for the shade when it gets too hot. To see where this gopher tortoise is heading here in Florida, I'm going to use this. A remotely controlled mini-camera on wheels with its own lights.
For years, scientists have been studying animals and their behaviours. We've tracked them using cameras, GPS and also radio sensors.
Using the latest scanning techniques, we can create a picture of the mound's interior.
And in our quest to learn more, we created animatronics.
SpyPup is the result of a huge amount of work in a small London studio.
Which are basically models of animals that can move mechanically, similar to what you might see at a museum.
Beneath the skin is a miracle of animatronic engineering. A skeleton of articulated metal limbs controlled by sophisticated electronics and servos.
We installed cameras in those animatronics and then placed them out in the wild to get up close and personal with the wildlife in their natural habitat.
The moves of the different creatures' real-life counterparts are programmed and tested. Each one takes months to design and build.
But as the age of technology progresses, scientists have found a much better way to interact with the animal kingdom using robots.
We are constructing robots the size of insects. Robots made out of entirely soft materials. We use nature to inspire the robots that we build.
Welcome to Moonshot, the show exploring the world's biggest ideas and the people making them happen. I'm Christopher Lawson.
And I'm Andrew Moon.
And in this episode, we're looking at biorobotics and the people who are out there designing robots that are based on the animal world.
But before we dive too deep into the cybernetic kingdom, here's a word from our sponsors.
Biorobotics, for me at least, is slightly different from biologically inspired robotics. So with biological inspiration, you're looking at biology and trying to use that to build a better robot. Whereas in biorobotics, part of their aim is actually to understand the biology by building the robot. So the robot is intended as a model of the biological system that you can use to test your understanding of how it works.
This is Barbara Webb, Professor of Biorobotics at the University of Edinburgh. Her fascination with insects has led her to build robots that are modelled after bugs.
Well, insects are very competent at a lot of things that robots are very bad at doing. Just in general, getting around the world, not getting damaged, being able to do everything from fly to swim to move on water, walk over rough surfaces, and do all that, in a directed way so that they're avoiding predators and they're catching prey and often navigating, collecting food and navigating over quite long distances very accurately. So there's a whole set of things that they can do in all sorts of different environments, and they have very tiny brains. So they must be doing something pretty good with those brains because they don't have supercomputers at their disposal.
And it's this drive to find out what insects do with those little brains which has led Barbara into the field of robotics.
One reason why we use robots as our model is that we want to try and capture all of that. So we want to understand everything from how they sense the world, what information they're getting from the world, how they're processing that, and then how they're using that to control their limbs or their wings or whatever system they're using to move.
All right, guys, I'm in position. I'm going to signal the ants.
Just like the creators of Ant-Man, Barbara has also developed an interest in ants, and more specifically, desert ants.
We do studies of ants in the field, so we actually go to a field site and follow the ants. You follow them with a camera, or we've even followed them with differential GPS system so that we can keep a track of where they've been. And we do different kinds of manipulations in that situation. So we'll pick up an ant from someplace and put it down somewhere else that may be less familiar, for example, to see what it's able to do from that position.
Most ants leave a trail of pheromones the moment they leave the nest, not just to find their way back home, but to guide other ants to likely food sources, which is why we see long trails of ants moving in the same direction. But desert ants are different in that they don't leave these breadcrumb trails, and part of the reason is because they hunt for food alone. Because the desert can be so hot and food so hard to come by, there's a good chance they won't find anything at all. And it's this ability to hunt for food on their own that Barbara finds so interesting.
They actually use visual memory, and they use integration of the distance and direction that they've travelled to keep track of where they are relative to their nest, which might be, hundreds of meters away and a small hole in the ground.
And it turns out that these desert ants actually have very little trouble finding their way home because they pack a whole lot of cool tech into those tiny little bodies.
They have almost 360-degree vision. They're able to see ultraviolet light, which we think might be quite important for how they recognize places in the world. And they can also see polarized light in the sky, which they can use as a compass system. So we'll try and replicate those sorts of sensory systems on the robot, and then program the robot with what we think is the control system, and then we see if it does the same thing as the ant.
There are so many traits in animals and insects that we could study and adapt from. But what can we really do with these characteristics once we've actually wired them into our robots?
I'd like to think the most helpful thing will be for using robots in more natural or unstructured situations. So if you imagine trying to use robots in agriculture where they're having to deal with, uneven ground and, vegetation that's not in any kind of orderly way that they can build a map and use a map to get around, they have to actually navigate with the kind of immediate surroundings. So I think it's in areas like that they might be the most useful.
So we have a wide range of sizes. So the smallest ones that we have are mainly designed to go into what we call confined spaces. So spaces that are difficult or too dangerous for humans to go into.
This is Navinda Kodagay, a senior research scientist at the Robotics and Autonomous Systems Group, which is a research group within CSIRO's Data 61. Navinda works on developing a range of robots that are modelled from insects, and it all started because of frogs. The CSIRO in Australia is a government-funded organisation that does a lot of research on agriculture. And as part of one of these projects, Navinda's job was to monitor frogs along a riverbed using some acoustic sensors. It didn't take long for them to realise that whenever they deployed these acoustic sensors, they were always in fixed locations, meaning Navinda couldn't track the location of the frogs as they moved around.
So these were very steep ravines where, and it was really difficult to access. That's when I started looking at legged robots. We bought some off-the-shelf platforms at that time, put some of our sensor payloads, started doing some testing. We soon realized the limitations of the off-the-shelf robot kits, and then that's when we started looking at designing our own robots.
The robots that the Data 61 team have built are based on a hexapod design. That is, they have 6 legs which allow them to move freely around terrain, and they can withstand angles of up to 45 degrees. Now, they also come in a range of sizes, from not much bigger than a dinner plate right through to robots which are 2 meters tall, making them perfect to send out on a mission to explore a forest landscape or into an area where humans just don't want to go.
An example is, let's say in the manufacturing domain, when they build aircraft, they still have a human crawling into the wing cavity of an aircraft to do the necessary checks and coatings and all of that. And as you can imagine, it's not a very pleasant environment to be in. So that's one of the motivating applications that we had initially to build a robot, a legged robot that can go into this sort of a space. And in the surveying and inspection domain, we still have to send people into underfloor spaces and to ceiling cavities to do inspections and to do scanning to figure out where the pipes and ducts are.
These animal-like robots would not only be beneficial for squeezing into tight spaces or monitoring frogs, but they can also help make rescue missions safer for both rescuers and those that need help.
If you think of the aftermath of a natural disaster such as an earthquake or a mine collapse, where you have extremely unstable terrain, you have unstructured terrain, those are the environments that are really suitable for legged robots, because legged robots don't need pathways or roadways to traverse on. All they need is fairly small footholds. And that means you can actually send one of these robots to carry a sensor payload that can help in locating survivors or communicating with survivors, and be able to even carry essential medication or that sort of essential things for people who are trapped in this sort of environment.
Right, so you'd be taking the risk away from the humans and then placing that onto a robot in these sorts of situations.
Yes, exactly. So even in the application of sending a robot into a confined space to do inspection, what we're suggesting is where we can put cameras, thermal cameras, lidars, all sorts of sensors on the robot, and then have a means of transmitting this back to a human operator or a human expert who can make the judgments and make the assessments from a safe and comfortable location, rather than putting themselves at risk at the hazardous location.
And while eventually these robots would be able to move through a location using artificial intelligence, at the moment you need to have actual people behind the controls driving the robot to its destination. So this particular robot that we're looking at is quite small, and it can sort of rotate on the spot. Its legs are just able to move around its body. You're controlling the speed that it moves, or are you controlling...
So we are giving a velocity command. So I'm providing the linear and the angular velocities at which it should move, and then it decides what gait to perform and how to move each of the joints to make it move forward, backwards, or to rotate.
Is it difficult to drive a robot like this?
No, this one is fairly easy. So it's used using a remote controller. So even you probably can have a go if you want.
Yeah, it looks like a PlayStation controller.
Yes, it does.
Yeah. Okay, so you're going to have to explain to me what.
Okay, so that makes it go forward, backwards, left, right, and this makes it rotate on the spot.
Okay, so forward, backwards, and rotate. Okay. Right. And then... That's so cool. It's really easy to move it around. How do I tell which way is forward?
That's an interesting one. So you're actually looking at the back of the robot there. So in the front, there's a camera.
So how quickly can it actually move?
Right now, we haven't optimized it for speed because we wanted it to go over a relatively rough terrain. But we can make it go a bit fast. At the moment, I think the top speed would be about maybe about 30 centimeters per second.
I imagined it being a much harder thing to control. And does the complexity change with the size of the robot in terms of being able to control it?
Not really, because we have a family of robots going from the smallest one to the 2-meter tall version. We actually run the same software base on all of the robots, which means it has pretty much exactly the same controls. But different robots do have additional functionality. Some of them have the functionality to use some of the legs to manipulate objects or obstacles. So then the controller would have some additional functionality for you to invoke that behavior. But in terms of just making it move around, it's fairly similar.
And we'll continue our look at these animal-inspired robots right after this break. Welcome back to Moonshot. I'm Andrew Moon. In this episode, we have been delving into the world of robotics based on how animals roam our world. And insects aren't the only creatures scientists and creators are drawing their inspiration from.
This is Plurobot. Plurobot is a robot that we designed to closely mimic a salamander species called Pleurodel swelt.
This is Alki Eisbert, who is the head of the Biorobotics Laboratory at the Swiss Federal Institute of Technology at Lausanne. He introduced Plurobot at a TED conference in 2015, and his source of inspiration for the salamander-like robot has a closer relationship to humans than you might think.
It makes a wonderful link between swimming, as you find it in eels or fish, and quadruped locomotion, as you see in mammals, in cats and humans.
Now, Alki is hoping to use his robot as a scientific device for improving neuroscience. And rather than only investing in engineers and computer scientists, the Plurobot team includes neurobiologists, because the team is actually hoping to better understand how animals move, specifically focusing on how the spinal cord controls motion.
A major component behind movement is the spinal cord, which has reflexes that control our sensory motor coordination. Even with the most advanced technology, it is still especially difficult to record activity in the spinal cord because it's protected by the spine. And understanding what happens in the spine becomes ever more important as we look to help people who have issues due to spinal cord injuries. But with a biorobot like Plurobot, studying the role of this activity and movement is made possible.
It's very important to understand how the spinal cord works, how it interacts with the body, and how the brain communicates with the spinal cord. And this is where the robots and models that are presented today will hopefully play a key role towards these very important goals.
Now, as we've mentioned on Moonshot before, Boston Dynamics is another big player in this animal-like robot space. The company created a laboratory prototype of a cheetah, and while it doesn't exactly look like the real thing, it certainly could give most humans a run for their money, reaching speeds of around 48 kilometers per hour, which is actually faster than Usain Bolt. Big Dog is another robot they've worked on. Its name is quite fitting since at 1 metre high and 109 kilograms in weight, it's much bigger than the size of your average Great Dane. Big Dog was made to go out in the real world. It can climb slopes, walk in the snow and water, and can even carry loads of up to 45 kilograms.
Boston Dynamics was sold in 2017 to robotics giant SoftBank, and that acquisition is already starting to see the company change focus to one of commercialization.
So Spot Mini is in pre-production now. We've built 10 units. That's a design that's close to a manufacturable design. We built them in-house, but with help from contract manufacturer type people. We have a plan later this year to build 100 with contract manufacturers, and that's the prelude to getting them into a higher rate production.
That's the CEO of Boston Dynamics, Mark Rabert, speaking at TechCrunch Disrupt in May, announcing that the company is going to start selling their Spot Mini robot in 2019. And that's a really big deal for a company that's mainly been sustaining itself through military contracts.
We're not saying what the price point is yet, but I'll tell you that this prototype, which if you just looked at it, you couldn't tell the difference from the previous one, but it's about a 10 times reduction in cost.
But as good as the Boston Dynamics robots are, if we look more broadly at the field of robotics and these animal-inspired robots, there's still plenty of room to improve.
So we have several implementations of the robot ant, or we sometimes call it the ant bot.
This is Barbara Webb again.
So we've been able to show that the basic mechanisms work, but what we tend to find is that it's never as robust on the robot as it is in the ant. So, for example, it will work for the robot as long as it's on a nice flat floor, but then if we put it over bumpy ground, that the ant is fine with bumpy ground and the robot stops working. Or, the ant can deal with the fact that the sun has moved in changing times of day, but our robot at the moment is not very robust to changing the lighting situation and so on. So what we usually find is, if we keep things simple enough, we can usually show in principle that the mechanism should work, but there's nearly always something that the ant can do that the robot can't.
Technology still has many limitations, but we're slowly edging towards a future where these robots are more lifelike than ever, and Navinder and his team at the CSIRO are constantly looking for ways they can improve their hexapod robots. They're brainstorming ways to come up with the best robotic legs, integrate the best sensors, and apply artificial intelligence techniques that will improve the overall functionality.
And the other one is trying to use machine learning techniques to allow the robots to be able to more intelligently navigate in an environment, be able to learn from its mistakes, like we humans would do. Like we'd let's say if we try to walk on a area that we've never walked on before, let's say loose gravel or loose soil or something like that. Initially, we'd be very cautious. We'll try to very cautiously tread that environment. But once we've done that, we actually have that skill in our skill repertoire, and we can use that if we see a similar terrain again. So we are trying to give our robots that sort of ability where they can kind of learn from their experience and be able to apply that knowledge when they see a similar terrain the next time. So these are a few of the different research topics that we are trying to address.
We really, have solved the problem of how to build the nervous system and a very compact machine that is very similar to what the nervous system does as a machine, if you like. But what we can't build is a equivalent of a muscle that drives the leg of an insect that actually operates, in anything like the same power, with the same energy consumption, with the same ratio of size and so forth. So there's still, we're in the mechanics, we just can't copy the mechanical capabilities of these animals at the moment, I think.
Do you think that's something that we'll be able to do in the future? Or do you think that's something that insects and animals will be able to retain for themselves?
No, I think it's possible, and it will probably come through new smart materials. I think that's probably the area where these kind of breakthroughs will come, but I think there's a long way to go to get something like that. So I think, relatively speaking, that's a very unexplored and new area.
In a way, then, the evolution of biorobotics is one filled with constant iterations and improvements. And for Barbara and others like her, there's this almost art-like appeal to her 2-, 4-, and 6-legged subjects, studying every element to understand not only how things work, but what might actually come next.
I think it's because you can't help but be impressed when you look at animals and what they can do. And if you've worked in robotics for a while, you begin to appreciate that more and more and more. That every time you see a bird fly or a cat jump, onto a high table from the ground, or for me now, even seeing a simple insect crawling across the floor, you can't help but be amazed at how robust and capable they are compared to anything we're able to build. So it may turn out to be something like, I think an interesting contrasting example is flight, where people spent a long time trying to build things that flew like birds and then only really made progress when they stopped trying to make them like birds, and came up with completely new principles. But I think if they hadn't been inspired by birds in the first place, it wouldn't have happened.
You've been listening to Moonshot, hosted by me, Christopher Lawson, and also Andrew Moon. Research for this episode by our intern, Caroline Ho. Our amazing cover artwork is by Andrew Millist, and our theme music is by Breakmaster Cylinder. Moonshot is a production of Lawson Media, a podcast production company. You can find out more about what we do at our website, lawson.media. And if you'd like to support the show, we'd love it if you could share it with at least one of your friends. The more people that we have listening, the more support we can get from advertisers, which means more content for you. And speaking of content, if you want to send us any feedback or give us any ideas for topics to cover on the show, or maybe you just want to say hi, send us an email to moonshot@lawson.media. We'll be back again next Wednesday for another episode, so whack on your augmented reality glasses and let's take a look at the future.